Yeah, welcome to our linked data party. This is our weekly highlight. On Fridays, we always gather and talk about the latest hot topics happening in the world of linked data. And I think the development of a new HDT implementation is definitely one of these highlights. So it's really great that you're joining. And so we also have many people joining from Triply. Because of course this is really relevant to our software, which is based on HDT. Yeah, we're really curious and excited to talk to you. So maybe I start with a quick introduction. I heard Wouter reached out to the two of you because you published this package. So thank you for volunteering to present it to us. And yeah, you also wrote a paper with your results. You also had a benchmark, I think. And I don't know how much you know about us. So we are Triply. We have our own database for RDF. And so if you want to play around with RDF, you can create your own free account. We are quite scalable, thanks to our HDT layer, I think. And we are also quite large. We have our SaaS branch, and we also do customer projects where we transform data to linked data and write ETLs. So I think that's our main topics. We're also, of course, doing a lot of modeling. We are quite close to the field. Having many interns for their thesis usually. So I think this year we had 7, something like that. So we are also interested in what's going on. And maybe I also introduce you. So we have, I hope I have this right. So we have Konrad and Tim. And Konrad, you're from Leipzig. I think your PhD advisor was Jens Lehmann, and that was at the Agile Knowledge Engineering and Semantic Web Group. And nowadays, I think you work for the Institute for Medical Informatics. Yes. Good research. And Tim is from the Freie Universität Brussels, and he's working on the intersection of database theory and systems, in particular parallel and distributed data systems. Yeah? Yes. Yep. Very good. Yeah, and you developed the HDT-Rust. So when Wouter asked me to do the introduction, I first had to ask what's Rust. It's a bit embarrassing, I guess, but I learned it's a new programming language. And I think it was originated in the Mozilla organization, and then many larger corporations started using it. And it has some advantages that other programming languages also have, but less disadvantages. So these are quite nice new language. And HDT, of course, all of us know. It's the header dictionary tuples. And it has a really tiny Wikipedia page, which consists of only 3 sentences. Refers to the data structure and format for serialization, which optimizes data compression while still making the media available for web navigation. So I think having said this, I share the link to the paper maybe.
Yeah, thank you.
I guess you already have the link. And then I think I would hand over to you, unless you have, maybe you want to introduce yourself or you have questions. And a preliminary, sorry, you wanted to say something.
I can I upload it? I'm using Google Meet for the first time, or should I just share my screen? I have it as PDF.
Yeah, you can share your screen. I think that's good.
Okay, then I will do that. Okay, I think this is here, present now.
Yeah.
And now it's I can now choose window and share, and I hope you now Do you see it?
Yes.
Okay,
Yeah.
that's great. So I've wanted to do a really quick introduction in case someone there maybe is not HDT expert in your attendance, like intern or so. So the idea is before we have, if we have a research project or an industry project, and at the end we have an RDF knowledge base, we want to deploy it, we want to share it, and of course we want to consume and query it. So the text-based RDF formats, they are quite large. If you have a large knowledge base, then you have a large file size. And of course, you can use a general purpose compressor like zip or bzip or whatever, but still you cannot query it in this form. So like the normal approach is you download it, you uncompress it, import it into a Sparkle endpoint, and then you can query it. And this is just like an example, basic like architecture of one of our research projects, where at the end we have an RDF knowledge base, and then we want to disseminate it because we want to write a paper, and the paper should get accepted, and of course it also should, like on its own, it should be well received by the users. They want to consume it, for example, using an RDF browser that resolves the URL and gives HTML or RDF serialization depending on the type of user. And the central element, I don't know if you see my mouse cursor, but the central element here is the Sparkle endpoint. And this is really cool because everyone does it this way, and you can use all the standard components, because in a research project, you don't have much time to do software development. So you use all the tools that are already there. You set up the Sparkle endpoint and everything works. But it also has quite some disadvantages. So it works until a point and then it crashes. And I guess in a company, you have like operational management where you maintain stuff. But in academia, it's often that you have a research project for a limited time, and then there's no one responsible anymore, and you don't have any more money. So it's very often that you see those knowledge bases, the deployments go offline, or they have like timeouts. And this is also because Sparkle can get quite complex, the queries, and there's also some overhead. And also, I think a problem is with Dockerization. So, I mean, Docker is great. I use Docker for everything now. I put everything in Docker, but it's a bit inelegant to use it with the Sparkle endpoint. If you have many of those knowledge bases and architectures, you want each to have their own endpoint, their own application server. You don't want to put everything in the same endpoint, because this is not good modularization from a container perspective. But yeah, so you have this failure point. And another way to use stuff, I guess, is also what you do, is you don't use the Sparkle endpoint to query, but you use an RDF library and embed it into your application. So this is just an example from our RDF browser, which has it embedded. And now you don't have the external dependency anymore. You have much more control. But the problem is, I always thought, okay, RDF libraries, they're really slow. So fortunately, there's a really quick one called Sophia for Rust. And this is log scale. This is the benchmark suite from the Sophia and developer. And you can see that even in log scale, it's a massive difference depending on which one you use, and also depending on the data set size. You can look at our paper or at the Sophia paper and see this in more detail. But I just wanted to share how much of a difference it is which library you use. So here, for example, we have 10 million triples, and we do a question mark PO pattern, so one variable and two constants. And we see that, for example, with Sophia, it's really, really quick. It's no caching or something. It's 20 milliseconds response for such a query. But on the other hand, if you go up in size, you have a large amount of memory consumption. And that is where compression techniques like HDT help to get the memory consumption down. Now, you actually see if you use Java that it doesn't give that much advantage in this case, like the the lowest memory Rust library, Sophia, has actually only a bit more memory consumption than HDT Java. But of course, if you go up in size, the distance goes further. And what I found also a bit interesting at first, I thought, okay, HDT is really quick. But then I thought, okay, Sophia is quicker. But at the end, I realized it makes sense. In a non-compressed case, you have everything there and it's quicker. But with HDT, of course, you have the decompression steps. So it gets a bit slower, but you have the advantage that you save much more memory. So I don't want to go into the details of HDT because you probably know it. You have this bitmap triples structure where you encode the triples as integers and then in this tree form. And then you have the object index to get efficient querying in both directions. And this already exists. So why are we holding this presentation? Because it didn't exist in Rust. And I think Rust is a great language for semantic web tooling because there's often a lack of tooling. This is really that it's easy to use, stable, and open source and performant. And I think Rust can do all of that. So compared to languages like Python and Java, it's really fast and uses a low amount of memory. Compared to things like C and C++, it has a lot of static guarantees out of the box. So I couldn't have done it in C++, I think. I mean, fortunately, Tim did all the hard groundwork anyways, and I just had to finish and test it and so on. But I just have a lot of trust in the Rust code because I know, okay, I won't get some kind of memory errors because the safe Rust prevents it. And also with the cargo tool, you have many tools out of the box. Like you have a formatter, linter, testing, benchmark, all of this stuff, which you can get for other programming languages, but first you have to decide which one do you use. You have to install it separately, configure it, and here it's all out of the box in language. It has modern features and a fast evolution, especially if you stay on the nightly channel, you can test drive. But if you want a more stable approach, you can also use stable Rust with the releases, but still you get quite new stuff quite often. And it's quite concise, which matters to me because I like to just work in a text editor and not use an IDE. And for example, with Java, it's really difficult. If you don't use an IDE like Eclipse, it's like a ghost town. You have dozens of files with interfaces in them, and you have to go around to find the actual stuff because it's also verbose and distributed. And I think that's what makes Rust fun is you have trust that it doesn't break in many ways. And it's also concise. However, it also has some downsides, like especially if you use libraries that make heavy use of traits, I find it really hard to understand how it works from an API perspective. You have to understand like the ownership and borrowing and the borrow checker. And because it's newer, it has less libraries. For example, it didn't have HDT in Rust. And also for this purpose, especially sometimes it's a bit difficult to do graph-like structures. So now I give the presentation to Tim. I guess you want to share from your own screen, right? So you
yeah,
can...
you can maybe just share and I'll tell you to go on. It's not so many slides. So I'm going to talk a bit about so I'm just going to talk a bit about how it got started and why I started building it. So on the next slide, I originally built this for my master's thesis. So I wanted to build a data log query language for RDF, so I could, which is a language that's very easy to parallelize, and you don't have to worry about too much locking or underlying structures that are difficult to implement. But I needed a lot of benchmark data for that. And in that case, I went looking around the web and I found a few places where there were HTTP data dumps with a lot of triples in there, and they were actually relatively compressed, so easy to download. I downloaded those files and went looking around into what HDT actually is, and noticed that there aren't that many libraries for it. So there was one in Java at the time, and I think in C++. But my implementation was in Rust, so I needed some way to get it into Rust, and then I started building it. Eventually, due to time constraints, I didn't get the implementation finished in time for my thesis, so I decided to focus all of my effort on the proof parts and the theory parts of my thesis. But I did wanted to open source what I had, so and that was incomplete. I isolated the HTTP part and put that on GitHub. And thankfully, Konrad picked it up and he made it actually usable. So he really did the vast majority of the work to get it up to the stage where it is now. So definitely props to him. Maybe the next slide here. So the basic architecture, it really resembles the Java and C++ versions. So I didn't do much reinventing there. And the architecture really has 4 major components. So obviously your API, which is the thing your programmers interact with. But then the model is how you represent your triples in memory. There is a section on this behind what I'm talking about. But, then we have the containers, which is how you compress how we compress like the string data, and how you represent the triple bit maps and everything. And you have a dictionary, which is your mapping between the IDs, which are now your triples, and your actual string data. So there are different kinds of these, and in the HDT papers, they go into more detail into which kind of dictionaries you can have, but I think we focused primarily on the 4-section dictionaries and just the regular implementation they described first. So at the initialization time, your goal is essentially to build some compact in-memory representation for your triples. Like I mentioned previously already, it's just 3 integers next to each other. That's really nice. I mean, you can load a lot of triples immediately into the cache of your processor in one go, because every triple looks the same. You don't have to worry about any of that. The first thing it does is just read your metadata, then you read your dictionary and your triple bit map, and then you build this wavelet index over it. And that allows you to really quickly look at different permutations or patterns for your SPO or triples. So you just select one of those and it will get you the other ones. And from there, you look into the dictionary. So if you go to the next slide, if you get a triple, you can look up into the dictionary which string values or which values correspond with these IDs. Of course, how do you compress those strings? The thing here is they use plain front coding. So the idea is that URLs always start with the same sort of pattern. So HTTP // and then a bunch of domain information, maybe the slash for your ontology, and then some other substring suffix. And the thing is you are only going to store the things that are unique, and all the other stuff you only store once. And that dramatically improves the memory usage, which is really nice. Once you get all those components back, you assemble them into one triple, and you have your full in-memory representation that you can use and send to the screen of the user. So yeah, that's in a nutshell how it works. But of course, there's a lot more to it. Yeah, which Konrad is going to discuss further.
Yes, I want to show 2 quick sections. First, the optimization of it. So one thing I noticed is that's really hard to figure out which part makes it actually slow. So it was necessary to do actual profiling to really go deep into the memory usage and CPU profiling. And for example, what helped was to reorder the loading. I mean, of course, you have many dependencies. Most of it is quite straightforward that you have to load it in a certain order. But here, this wavelet matrix, it caused quite a lot of RAM peak consumption at the start, because it was done at the end of the loading process when the RAM was already quite occupied from the other stuff. And this is a bit dangerous, for example, if you have a server and on the server you restart it and all the things load in HDT file, and then even if you have enough RAM, maybe it can go out of RAM if everything loads at the same time. So in this case, the RAM consumption got lower by actually reordering it. So the wavelet matrix is now generated early. So from more than 5, it went down to less than 5 gigabytes. And it was like a lot of small tricks like this to get the RAM consumption down. And then I also had to do a lot of profiling to find out what was actually taking much time. And here this is a screenshot from Firefox Profiler. So you can with Rust use perf as a profiler and then convert it to a format that can be read with Firefox Profiler. And here, this is how it looks when something works quite well. You see a lot of like core methods of Rust or libraries you use, but not some loops or some things that take unnecessary time. And it's also possible to do some parallelization. Here you see 2 different threads. So the generalization of the generation of one of the helper structures here is done in parallel, and then the thread is joined later. And yeah, as the last part, I also want to show a part which is surprisingly hard in Rust. So Rust makes some hard things doable, but I'm interested in your input. Maybe this is actually absolutely not an issue with C++ or in your library, but this is actually a question that gives me a bit of headache sometimes. It's how to actually do the API serve phase and how to actually return triples to the library callers. So of course, like a library doesn't have to be as intuitive as an application. Like the users are already experts, but still you want to make a library that's used by people, and it should be as easy as possible. So the first step, okay, let's assume we already have some structure to hold our string triple. So how do we actually return it? Which kind of collection we use? So formally an RDF graph is a set of triples, and we query using triple patterns. So we get, again, a subset of RDF triples. So we could return a set of triples, but would it make sense? Wouldn't make so much sense, because we may only care about a part of the results, and all the processing needs to happen at the start. So you could imagine that maybe you have some kind of parallel streams going on. So you have some component that supplies the triples, and some other component does some processing on it. And it's hard to parallelize if you have to generate the set first. So, and also all the memory needs to be resolved all at once, which can matter if you have really big result sets. So this part is actually easy. Okay, we just use an iterator of triple. And so what do we have as an API? The main API right now is this. We have a method triples with pattern, and this for not Rust users is a lifetime. It just says that the input parameters have a shared like scope where they live. And we have an option. An option can be sum and then a value or none. And you have the subject pattern, predicate pattern, and object pattern. And when it's none, it means in this case that we want to get all. So for example, we want to have all German cities. We say SP is the URL of Germany. This pattern would be the URL of Hesse country, and this would be none. And then we get all the countries in Germany. And we get this as an iterator. Okay, but how do we actually represent the triples? Well, okay, we have the bitmap triple component, we decompress it, we get the ideas and IDs, and then we have triples in the sense of 3 tuples of integers. Actually, we use usize because it's like a standard Rust output value for all the array indexing methods and so on. But in the documentation, they use, I think, unsigned 32-bit values. And in the Java version, they use signed 64-bit because they don't have unsigned values. So, okay, so do we actually represent the triple now as a 3-tuple of strings? Well, it makes sense in Java. In Java, a string is immutable. It's not a primitive, and all the non-primitives are actually references. And if you have duplicates, of course, you have to program your code correctly that you recognize those duplicates. But let's say you have a SP question mark pattern where S subject and predicate are constant and the object is a variable, like in the example with the cities. So Germany has city, and this is the list of cities. And then you have a lot of duplication if you allocate a new string for each of them. But if you handle this correctly, then it works. And you don't waste space because you can just return the same string multiple times. And yeah, and also if you return it and it gets garbage collected when it's not referenced anymore. And when I was still coding most of the time in Java, all of this was like completely natural to me, and I didn't even see what a big benefit this had. But this was one of the cases where I actually noticed it. So when I switched to Rust from mainly like Java and JavaScript, most of the time I actually didn't miss the garbage collector. Like in Rust, they have this ownership rules, and if something goes out of scope, it automatically gets collected. It actually works quite well in most of the real-world cases, but yeah, this was one of the cases where I'm glad I have the garbage collector in Java. So if you look at the Java implementation, it's like what they do. Of course, they don't use string, but like the interface char sequence here, but it's the same principle. We have like this triple string with 3 values, and they have like some custom implementation where they only use 1 byte per char because Java has 16-bit for the Unicode values. And they have this notion of the delayed string, which kind of throws off the benchmarks, which is why I had 2 rows in the benchmark table. And then they have a bit of like this delayed string. It gets converted to a string when you first use it. And then they have a dictionary translate iterator buffer, which is quite interesting, where they fetch, I think, 1,000 elements at the same time, and they have a map from long. This is the IDs, and this is a char sequence here. And with Java, it's not a problem. You don't own something in the map. You can just return it out of this map. So, okay, how do we do it in Rust? Like in Java, it's absolutely no problem. Works out of the box. So a string in Rust is kind of like a pointer to the heap. It may grow, so we have an extra capacity field which uses in one extra 8 bytes in 64-bit machines, which the library only supports. And we can use alternative box string, which uses 1 U size less, but then maybe it's a bit confusing to the users that they don't get strings. But this is not a big problem. But the problem is the string in Rust owns its own contents. So we cannot like have multiple strings which share their content. So in those 2 triples here, if you have the same string twice, then we would actually have to allocate the memory twice. So, okay, you may think, yeah, just use a pointer. Rust has pointers, but they are not really guaranteed to point to wallet memory. So it's possible to create pointers in safe Rust, but not actually use them. They are not automatically cleaned up. They don't move the ownership. And yeah, we want to do everything with safe Rust. So of course, I guess the C++ programmers will now think, okay, just use references. Which is like a safe kind of pointer, which you use most of the time in Rust if you borrow something, and I mean, if you reference something. So here you create a new string and you convert it to a string slice, and you cannot return it out of the function. It's a bit of a problem. So this is one kind of those problems which normally you don't have, but in this specific case. So normally, I also talked with the author of the Sophia library. It wasn't a problem for him because he says, okay, you can just pass your database object in with a lifetime, and you can return references to that, but it doesn't work in HDT because the resources only exist in compressed form. So then the Sophia author, he had this thing called maybe own string. It uses unsafe Rust to do some crazy magic to have a string that is owned or borrowed. But you can use unsafe components in safe Rust. It just means that they are responsible to check that everything is okay. But under the assumption that they take care of everything, you can use it as much as you want. So this can either be a reference or an own string. And for example, now in the case of this SP question mark pattern, you can just return a reference to your input parameter for the subject and predicate, and the object is just an owned string. So, okay, this works for this pattern, and I mean, there are 8 patterns for those with like 1 variable and 2 constants, but it doesn't work if you have, for example, all triples or generally patterns with multiple variables, because then you don't have the reference you can get back. But at the same time, you get duplicates. You can have the same subject, predicate, or object multiple times. So then Rust has reference counting and atomic reference counting smart pointer. Here the atomic one is used because in our RDF browser we used Actix Web, and which is multi-threaded. So this one, it has like a counter, an internal counter, and also does synchronization. So you have some overhead. It's not optimal for patterns like the SP question mark, but you can, if you program it correctly, save space on something like the triple question mark pattern. So this is the best compromise right now, but I may change it in the future. Maybe you have some input on it, what to use. Another method would be to just give the people just the integer triples and along a method to use the dictionary, but that would make the library more complicated to use. Or for all 8 triple patterns, we could also have 8 different functions, which would have the best performance optimization potential, but it would be a bit cumbersome to implement. There would be lots of code duplication. You would have different kinds of string types in the output, which would really be complicated for the library users. Yeah, that's all I want to share, and I'm happy to receive questions on this, and Tim certainly as well. And if you want to check it out, you can use the crate or read the paper or give us an issue or pull request at the Git repository.
Yes. Oh, thank you so much. And do we have recommendations on the headache? That was my question. So, Eirik, did you maybe have some intuition how you would solve this? Eirik is our HDT specialist. One of our HDT specialists.
Yeah, I spent some time working on the HDT internally in Triplet for the last year or so. For us, it doesn't really seem like much of a concern to keep the memory usage of the uncompressed form of triples low. I think a working assumption has been that once you start deserializing, you should consume triples in such a way that you should be mindful of the number of triples that you keep in memory at a time.
So you don't like have often queries where you get like all triples from the knowledge base at the same time or something. Doesn't like happen often.
All triples from a knowledge base would often be too large. We do have cases where we buffer many triples, but there will always be some limit to how much we can buffer, and I guess that's the reason for why we have not. But there will be a limit, and we could increase it by a constant factor, but not beyond that. And I think that's why we haven't been focusing on decompression at this stage. Sorry, at the compression in this stage.
I guess.
Sorry, one more.
I guess that's the advantage. You have the actually experience of the usage, because for us as library authors, you don't know how the people will actually use it at the end and what their use cases are that you should optimize for.
I think it also depends on whether you manage to load all the data in memory while querying it or not. So it wasn't clear to me whether when you say loading the data, do you load the whole HDT into memory and then use it?
Yes, yes. It's not made. It's because I thought, okay, we could do like mirroring on the hard drive or SSD, but at this point it would just be like another database or something. And I thought it's better to have its focus as in-memory store.
Yeah, because we noticed that for our use cases, this is actually impossible because the having all the HDTs in memory for the data that we want to query is too much of a hardware footprint. So that's then I think also an answer to the memory question on results, that the result sets are also too large to all keep in memory. So we just stream through it, and then it's not a problem anymore.
Mm-hmm.
And I was also really curious because it seems that you worked a lot on querying HDTs. Have you also thought about generating them from string data?
I haven't. Right now, it's just the focus on just like read only. But maybe Tim, did you think about it?
No, not yet, at least. But yeah, to get back on the not fitting in memory. I mean, yeah, there's a lot of work in the databases side of things to have these databases that can perform like they work in memory, but then offload certain regions of your data back to disk. And then it would be interesting to see if some of those techniques can be applied to this library to make it like deal with the in-memory issue. I'm referring to Lean Store. It's an implementation of a database by people in TU München, if I'm correct. And they have some very nice techniques to deal with in-memory stuff. So yeah, maybe that's something in the future we can look at. But yeah.
One such technique might be memory mapping. That is something which is used in RDF CPP. Is that something you consider?
So yes, it can work for read-only. But the issue is the moment you start memory mapping and you deal with multiple threads that start to write, you get issues because you need to be careful with consistency, and because you basically delegate that consistency to your operating system, and which has less information about your use cases, it could end up doing things you don't like corrupt your data or something. So that's why mostly databases don't use a map in that way. But if you are sure that the data is mostly read-only, it's completely fine to do that, I think. But yeah, so the techniques that Lean Store, for instance, uses is to have just a buffer pool of fixed set pages with data in it. So in that case, they're tuples, but not triples. The ones that are used frequently, they stay in memory, like a sort of cache. And then the moment you have pages that are not accessed frequently, they just start to get flushed to disk. And oh, it seems like my connection has dropped.
No, I can hear you perfectly.
Yeah, but my screen has gone black, so I don't see any of you. Sorry. Well, and I guess that's just what I wanted to say about it. Like, so you have to really be careful with concurrency when you start to allow writes, and mmap gives away a lot of control there.
I think a main difference between our efforts is the target group. So we are using and developing HDT only internally. That gives us a lot of control over the data sources and also the data consumers. That allows us to take some shortcuts and to ignore some problems, which you, of course, need to think carefully about with a public package.
I think we lost Tim.
Yeah.
Oh, yeah, and I also think it's cool to have a library that's like more focused and say, okay, we explicitly don't support things like memory mapping, and then especially if you're only 2 people, then you have less complexity to maintain. And, yeah.
And so you mentioned that you're open source and always happy for contributions. What would your next item on your wish list be?
I would have to go to the issues, but I think optimization is always useful, like people really using it, because right now our RDF browser is the only really use case, and yeah, would be if someone just used it for something and has real world data and can say, okay, this part is really slowing us down, or this part is really where we use too much memory, would help. And also some because I'm not normally a low-level programmer, like sometimes people come in and do pull requests and they can do optimization of like the checksum calculation, something I have no idea about. So I think just if someone experienced would just go over the code and do a code review, I think they would find much to optimize actually, because that's not my expertise. Yeah.
Unfortunately, I think the crowd you're talking to is not experienced with Rust development either.
I guess people who can do C++ can also do Rust. I'm not sure I will.
And you work in C++ mainly, right?
Yes, our our HDT development is purely in C++. We also have some bindings to Node.js, since most of our data consumers are Node.js libraries.
And are you happy with the choice? Does it have some like challenges? Or because for me, I'm not a good C++ programmer, and if I touch it, it just everything crashes. And I would be interesting like how you do it, that because I guess you have to make everything stable and not crash.
Yes. So if we would start from scratch, I'm not sure if we would have chosen C++. But so the reason for why we use C++ is actually historical. There's an open source implementation of HDT CPP, and we made we forked from that essentially. And we have in recent years spent a lot of effort on modernizing this code base and also learning C++ in order to do so. Yes, also we've been learning about everything around C++, like package management and the development infrastructure around C++ build tools. So there's a large cost to using C++. When you presented some of the benefits of Rust, I get warm feelings of. It sounds very nice. The built-in package management and the built-in memory safety. It's things that I miss.
Okay.
Oh, by the way, Wouter here. Sorry, in the first part, I was indeed also joining in a different call. So Katrin, yeah, she knows how I do some of these things. But I did also follow some of the presentations. So thank you, by the way, for joining today. That's really cool.
Thank you for the invitation. It's really cool being here.
No problem. I also have an opinion on C++, if only because I used to be a computer scientist in the past. I think the main issue that we run into, and that also Eirik is correctly emphasizing, is that the C++ HDT implementation was written in C++ 98 with a couple of features from C++ 11. And for people who don't know, this actually refers to the year 1998 and to the year 2011. So yeah, I think Eirik and part of the development team has done some effort to move more towards C++ 2011, 2017, and maybe even 2020. Like C++ 20 is becoming more and more supported by recent GCC versions. And then basically Rust and C++ come very close, because then the defaults are always inverted in C++. So by default, you shoot yourself in the foot. But in the modern versions, you can actually do sensible memory management, and you actually do have a functional first standard library. I think that's also the main benefit of Rust. The main benefit, I think, of Rust is that it started later, so that it has a younger community, and it has a community that understands modern production systems. So package management is terrible in C++. And it's not terrible because it has to be terrible. It's terrible because the community is very, well, I don't want to say any judgment on the community, but the community is not very, let's say they're all over the place age-wise. And some of them, they really don't understand why you wouldn't just do a full source copy of the files in your project. And that's your dependency manager, right? And there's really people in the C and C++ community that seriously don't understand the benefit of the container system that Rust has. I think that's the main downside of C++. It's basically the community. But I had a different question, because I'm very curious, of course, to see a new HDT implementation after 10 years, right? The original one is from 2014. I had already given up on HDT becoming a sort of mainstream protocol. But since you are implementing it almost a decade later, what were the major innovations that you applied? Because there's been a lot of research, obviously, in the last 10 years. Computer science moves really fast. So what is your most relevant delta relative to the older implementations? And then I'm not talking about the programming language, but more about data structures and algorithms.
I think this would be a better question for Tim, who unfortunately, I think, dropped because he did all the baseline, or is he maybe back in? I don't see him, this picture. No, because I mostly did like the on top stuff, like the API surface and so on. So it's hard to say from my perspective, because I also just like looked at the libraries which are available. So I think maybe I could say this is good. You have, at least in Rust, you have you don't have to implement all the data structures with rank and select for yourself. You can just pick a package. And for example, I used, instead of a wavelet tree, I used a wavelet matrix, which should scale better in some cases. But other than that, I think it would be a better question for Tim, because he did like the low-level things.
And more from a high-level perspective, like 10 years ago, most data sets didn't use graphs, but these days maybe named graphs could have been a feature from the beginning. Like we do HDT, but then we also want graphs, or we also want read-write. Were those things maybe considered from the beginning, or are they maybe being considered now?
I'm also not sure about it. I haven't needed the graphs that much, the named graphs.
No, me neither. And often the use of named graphs in practice is often nonsensical, but it's very difficult to convince customers of that. So we have lots of like linked data savvy customers who use one graph per record, for example. So they have millions of graphs. And it doesn't make sense to explain to them that that's a wrong way of modeling, but that may be something that you have. I hope you have better users of your HDT implementation than people who come up with 6 million graphs on the first day.
And, I would be happy to get users in the first place, right? Right now we are our only users. So
okay, but then I'm going to continue on that topic. So I think HDT is the only way in which you can host the lot cloud. If you want to go past this individual database. Hey, Tim.
Maybe Tim can answer it now.
The internet at my lab has broken down, so I'm on my 4G. Sorry.
No problem, Tim. Just a quick question for you. Since your HDT implementation was implemented almost a decade later than the original one, what is the main delta functionality and data structure wise in your re-implementation?
I don't think much has changed there, but if I would have to re-implement it now with the knowledge that I have now, I would actually start looking at index data structures from the database world. So one of these things, one of the trends that I currently see is prefix tree indexes. So these are indexes where you start to build the tree based on the key instead of doing B-tree style things where you have key value pairs in the leaves, in the nodes, and then you just do binary search on them. You just have a tree where the key is the path. There are very cool optimizations there where they linearize those trees into long arrays, and then they can do SIMD operations to search each level in the tree using a constant number of instructions. So doing that, they managed to make certain lookups in that vastly faster than any B-tree could achieve. And they even beat out hash maps in certain cases, and they specifically built that for string data. So I would like to see what happens if you apply those techniques and with the things that HDT does and to see which performance comes out of that. But yeah, there are not many implementations of that again, because it's very recent research. I think it's also a paper from TU München. And I can send a link for that in the chat if you want. So that's the primary thing that I would want to try out, actually.
Could you send the link to that?
Yeah, I will. I have to look for a second, sorry.
And I think there are also some more recent HDT papers which are not implemented yet in the Java and C++ libraries. Like I think there's HDT++ and something else.
Yeah. Indeed, there's also some work under the name Trident, which is using different data structures, like more modern data structures that originated in the last decade, but applied to the same idea of indexing a dictionary and a graph. Thanks, Tim, for sharing.
So that's the repository, the paper I'm trying to look.
And maybe more of a community question. So for the longest time, I think, there was a very small community around really scalable linked data infrastructure. I think Triply is one of the few companies in that area. There's a couple of people in academia helping us out. So there's some people working on the Java side, and now also at least 2 people working on Rust, but soon probably a lot more. But from the community perspective, how can we convince the community that this is important? Because without this kind of infrastructure, we will never be able to host the lot cloud. And the lot cloud is much bigger than your traditional Oracle database. It's like the whole world becomes a database, right? So from a community perspective, like what do you see as sort of the future to collaborate more on that more like linked data vision?
I think one approach would be to focus on maintenance and long-term availability, because now the semantic web is old enough that we have many projects in the past. And especially in academia, it's so often that you have like some ransomware attacks or the old servers go down, and there's so many old data sets that are not available anymore. And I think it really sometimes even like websites of the institutes go down because there's some old stuff which is based on RDF. And I think this is a thing people understand. They see, okay, the stuff needs to be visible. And if we use the approach based on Spark endpoint, okay, it's really cool and it's a standard, but I think it shouldn't be that 50%, or I don't know exact figure, but many of the old projects, the deployments are not there anymore. And I think there you can get cooperation. Like if you just have some cool technical underpinning, no one is caring. But if their stuff goes down and you say, here, I can put it up really quick because I have some scalable solution that runs on your server and it's stable and hosts your data. I think that's how you get people to just convince them that you have a stable performance solution for long-term maintenance.
Yeah, that's also a pitch that we've been trying to make. So Triply is involved in providing the research infrastructure for the humanities in the Netherlands, called Claria, but also for the social sciences in the Netherlands, called Odyssey. And just to be clear, these are all the humanities scholars and all the social scientists in the Netherlands. They all have to make use of this national infrastructure. But even there, it's very difficult to pitch this idea. So I have also tried with the Archiving Institute for Research, DANS, in the Netherlands, but every nation state in the EU has it. There's also an EU initiative on this, of course. Fair papers also require fair data. So there's a lot of entry points to that vision, but also I've noticed it's quite difficult to get traction there. Whatever the case may be, if you ever need a commercial project partner to implement, let us know. And if we ever need to see the opportunity for such a research innovation, I'll also know how to find you.
That would be cool.
Those are my main questions. So really worried about the community and how this will move forward, but also really excited that there was this big, completely unknown to me innovation coming from the two of you. So congratulations for just coming out of nowhere with this cool innovation that I hadn't expected anymore. So I was really interested to see this.
Thank you.
Thanks.
Nice. Do we have any other last questions? We have 4 more minutes. No? Okay, then I would say thank you so much. That was really a lot of fun. And yeah, also a nice example of the power of open source. So I wish you many pull requests.
Thank you.
And hope to see you around.
Okay.
Good. Thank you. Bye.
Bye.
Thank you. Bye-bye.
Bye.
Good day.